Hey everyone, welcome back to another lesson in Math 2. We've been talking about the idea of radicals over the last couple weeks, simplifying radicals, how to combine radical expressions by adding and subtracting, multiplying and dividing, rationalizing the denominator was a big one. We're going to move into a new lesson that's still dealing with radicals, but a very specific kind of radicals called imaginary numbers, okay? I know you think, you hear the word imaginary and you think, well, so does that mean it's not real? In a strict definition of a real number versus an imaginary number, no, it's not a real number, but it is a real thing in life, okay? They shouldn't have really ever named these things imaginary. They should have come up with a different name for it. But anyways, with that said, our goal is to be able to simplify expressions, both sums and differences and multiplication, using imaginary numbers or using complex numbers is what we talk about. But with that said, I don't need you to write this down. I don't want you to write this down, but I do want you to follow along with it. Solving each one of these equations, we're not going to get into solving right now in depth. That will be next unit. But I do want to introduce it because it's going to show something about imaginary numbers. So in each of these cases, you should be able to solve these using the skills that you have from Math 1 or from Algebra 1. So in the first case, the goal is to get, in all cases, the goal is to get x by itself. Again, I don't necessarily want you to write these 4 examples down. I just want you to see something about it. So our goal is to get x by itself. In order to do that, we need to get rid of the square, and we need to get rid of the -1 or the -1. Remember, we do order of operations backwards when we go to solve for equations or solve equations, solving for x. So the first thing we're going to do here is we're going to add 1 to both sides. Remember, whatever you do to one side, you have to do to the other. So in this case, we get x squared equals 1. Well, how do we get rid of the squared? We get rid of the squared by square rooting. So we square root both sides. Well, what's the square root of 1? That's what we've been doing over the last few lessons, is dealing with radicals. That's why it's here, okay? That's why we've been talking about it, because of these specific type of problems. So that, remember, the square root of 1 is either 1 or -1, the principal root and the negative root. We write it like this. We write it as x equals plus or minus 1. That's what that means. +1 or -1. Okay, so let's go ahead and take a look at B. Well, the first step would be to add 25 to both sides. And so we end up with x squared equals 169. To get rid of the squared, we're going to square root. And so the square root of 169 is plus or minus 13. So that's fine. But C and D, we're going to see something unique. We're going to see something different. To get x by itself, we have to subtract 1 this time. And so we end up with x squared equals -1. And then in order to solve for x, we need to square root both sides. Well, what's the square root of -1? What number times itself gives you -1? Well, within every number that you know of, there isn't one. There is no specific number times itself that will give you a -1. Why? Because if it's the same number, that means it's either both, the number is positive or it's negative. So if I have a positive times itself, that means a positive times a positive. Well, positive times a positive is a positive number, not -1. And if I have a negative number, a negative times a negative is a positive. So I don't get -1. There is no number that you currently know that will give us the square root of -1, okay? So right now, as of right this second, we don't know. We can't say what the square root of -1 is. So let's look at D. Well, the first step here would be to subtract 150. And we end up with 3x squared equals -147. And then from here, we have to divide by 3 because we have to get rid of that multiplying by 3. And so we end up with x squared equals -49. Then we square root both sides. And again, what number times itself can give you a -49? I know you're thinking 7, but 7 times 7 is +49. Well, what about -7? -7 times -7 is +49. Well, what about -7 and 7? Well, yeah, -7 times 7 is -49, but remember, it has to be the same number. And 7 and -7 are two different numbers, okay? So we don't know. We don't have an answer for this right now, okay? And that is the idea of imaginary numbers, okay? So now let's go ahead and take a look at something else. Again, I don't want you to write this down. We're just exploring this idea. I want you to follow along with it. So you can see in this expression that we have the square root of negative 15 in both of these terms. Now, if there's no such thing as the square root of a negative number, then this equation cannot be a valid equation. It can't be possible, okay? But I'm going to show you that it is possible, okay? So here we're essentially multiplying binomials. We've done that. Remember, we separate the first one and we distribute both of these into the second one. So we rewrite this as 5 times 5 plus rad negative 15, 5 times 5 plus rad negative 15, and then minus radical negative 15 times 5 plus radical negative 15. From here, we'll distribute, so we end up with 5 times 5, which is 25. And then we get 5 times radical negative 15. We can't multiply those because one's outside the radical, one's inside, so we'll just write them next to each other. We get 5 radical negative 15. And then in the next one, negative rad negative 15 times 5. Well, the 5 is outside, so that's going to go in the front. So we end up with negative 5 times radical negative 15. And then this part is a little tricky. Negative radical negative 15 times radical negative 15 can be rewritten as negative radical negative 15 squared. I know a lot of weird words here, but the bottom line is we're multiplying this radical times this radical. And because they have the same inside number, the same radicand, we can write it as a square, right? If I say 5 times 5, I can rewrite that as 5 squared, or 7 times 7 is 7 squared, or x times x is x squared. Well, here, radical negative 15 times radical negative 15 is radical negative 15 squared, okay? Now, if I go to simplify this, there's a couple things that simplify. First thing I notice is that I've got a positive 5 radical negative 15 and a negative 5 radical negative 15. Those are like terms because they have the same radicals. One's positive 5, one's negative 5, so how many do I have? Well, I don't have any. So those are going to cancel out. So I end up with 25 plus, and all this is gone, right? Now here, where did I get the minus negative 15? Well, the radical and the square cancel each other out. Let me go back for a second to the previous slide. The reason we square rooted, like on part A or part C, we square rooted is because we wanted to get rid of the squared. The squaring and the square rooting operations are inverse operations. They cancel each other out. That's why we end up with x. So if we go forward to what we were talking about here, we have a radical that's being squared. Those are inverse of each other, so they're going to cancel each other out. And so we're going to be left with whatever's inside. So we're left with minus the negative 15. And so 25 minus negative 15, that turns into 25 plus 15, which is 40. So the point is, I just worked with this expression, and I'm not asking you to understand that fully, but the idea is that I worked with this expression and I simplified it to end up with 40. Now, if the square root of a negative number was not a thing, if it was not possible to work with, if it didn't exist, other than me just writing it down, then I wouldn't be able to do any math with it. But I was able to do math, okay? And so here's the idea. And again, you don't have to write this sentence down, but I think it's an important one to discuss, okay? If the square root of a negative number does not exist, how is it that we can work with it and get an answer that does exist? Well, the reality is this. The square roots of negative numbers do exist. They just don't exist within the set of numbers that we currently know. And here's the example that I would give you, okay? Just like negative numbers only work within specific parameters, imaginary numbers only work within specific parameters, okay? So here's an idea. If you think geometrically, if I were to ask you how far it is from one place to another, or how long this line is, right? The answer is always going to be a positive value. The distance between 2 points is always some positive value. You don't say the distance is negative 7 feet. You say the distance is 7 feet. There's no negative values when you're talking about distance. There's no such thing, okay? There's no negative values when we're talking about distance. Same thing with the number of apples. How many apples do you have? Well, I have negative 5. You can't have negative 5 apples. That's not possible. You can have 5 apples. You can owe somebody 5 apples, but you can't have negative 5 apples, okay? So there are these negative numbers that we can apply to different contexts, right? And that's why we have them. In the same way, we have imaginary numbers that apply to specific contexts, but they don't apply to everything, okay? So now with that said, you're going to want to write this down for sure, okay? This last sentence. The imaginary unit, write this down. We define the imaginary unit as this. The square root of -1 we call I, okay? It's a different set of numbers altogether. Anytime you see a square root of -1, you get I. Write that down, okay? Now, what does that mean? What can we do with that? Well, if I have I is equal to the square root of -1, just like I said, what happens if I square both sides? So in other words, what do I get when I have I squared? Well, in order to go from I to I squared, that means I have to square both sides. I have to square this to make it say I squared. And remember, whatever you do to one side, you have to do to the other. So on the other side, we end up with the square root of -1 and then squared. And so as a result, you can see the square root and the square cancel each other out, and we're left with what's inside the radical. We end up with -1, okay? This is so hugely important, okay? The two things that you need to get from this right now is that I is the square root of -1 and that I squared is -1, because if I square this, I end up with -1. These are two things that you're going to want to commit to memory, especially this one, and then you should be able to manipulate this one so it says I squared equals -1. Write that down. It is important that the square root of -1 is I, and that I squared is -1, okay? Now, what does that mean? What can we do with this? Well, here's some examples, okay? We want to simplify the following, okay? The first one says, what is the square root of -50? Okay? A is the square root of -50. Now, this is an example, so I do want you to write down these things from here on out, okay? The square root of -50. Well, we know how to simplify radicals. We've done that. We've done that for a few days now. How do I simplify radicals? Well, I factor. I do a factor tree, or I do the cake method, or whatever I do, I factor. So I'll go ahead and do that here. I've got -50. Now, whenever you see a negative number, one of the factors is -1. So I'll do a factor tree. -1 is one of the factors. What's left over? Well, it'd be 50. -1 times 50 is -50. Now we factor the 50 just like we normally would. 50 is 5 times 10. And 5 is a prime number. So we can circle that one. And notice -1 is at the end of the branch as well. And then 10 factors to 2 times 5. And both of those are prime numbers, okay? So we're going to approach this the same way as we did before. The square root of -50 can be rewritten as the square root of -1 times 2 times 5 times 5. Okay, so that's the same thing. And we check our work. We multiply that out to make sure we get -50. -1 times 2 is -2. Times 5 is -10. Times 5 is -50. So we know we did it right. Now, what do we do from here? We do the prison break thing. We simplify the radicals. We look for pairs. Well, here's a pair right here. So we know that we can take that out. So we know that we can take a 5 out for sure. Now, I'm going to put the square root, and we say, well, what's left over? What's left over is the -1 times the 2. But we know something. We know that the square root of -1 is I. We just wrote that down, okay? So the square root of -1 is I, which means if you have a -1 inside the radical, you don't need a partner to take that out. You don't need a buddy to take that out. It just becomes I. So it escapes and becomes I. So we could put 5I here. And then what's left inside is the 2. And so we're left with, as a final answer, 5I radical 2. Okay? Because I is the square root of -1. This is how I kind of jokingly say it, right? When we're talking about a prison break, you have to have a partner to try and escape. But if you're an imaginary number, you don't need a partner. You can just walk through the wall. You can just escape on your own. It's just as you walk through the wall, you transition from -1 to I, the imaginary unit. That's just a quick way to remember it, I guess you could say. It's like a ghost. He just walks through the wall, okay? But anytime you have the square root of a negative number, you factor it down just like you normally would. You should have a negative 1. And when you have a negative 1 inside the radical, you can just take that out and it's I, okay? You'll see why this is important later on. There's a lot of higher level math dealing with imaginary numbers. Electrical engineering and the process and the movement of electricity deals with imaginary numbers on a higher level. So you may get there, you may someday see that, but we will also see it in our future math classes and what we're going to be doing in the next unit. So it is important, okay? All right, for B, we have the square root of negative 147 a squared. Okay, we're trying to simplify this. Well, we're going to factor it just like we normally would. We know for sure that we have a negative 1 in there, so I'm just going to write that down. And then I'm going to do my factoring tree off to the side. And I can put the negative 1 here, that's fine. Negative 1 times 147. And then 47, well, that's not divisible by 2. How do I know if it's divisible by 3? If I add the digits, 1 plus 4 plus 7, that's 12. 12 is divisible by 3, so I can divide by 3. 147 divided by 3, that's going to be 449. 3's prime, 49 factors is 7 times 7. So our prime factors, negative 1, 3, 7, and 7. So I already have my negative 1 there. I'm going to put my 3, my 7, and my 7 there. Now notice I still have the a squared. Well, what does that mean? That means a times a. A squared is a times a. Now we're going to circle our pairs. We've got a pair of 7s and a pair of a's. So we can take those out. 7a. And then inside the radical, we have a 3. What happens to the negative 1? Well, that guy goes out and becomes an imaginary number. So we write it as 7a I square root of 3. Now, a represents a real value, like the number of something. I represents a specific value. A is like a variable. It could be anything in life. But I is a specific value that we already defined as the square root of negative 1. And so that is how you do that, okay? Now, with that said, let me check my work, make sure I'm right, and it appears to be that I am. So what I would like you to do is try these two on your own. The first one, you're going to want to simplify the inside first and then simplify the radical. But go ahead and do it and then push play to see how you compare to what I did. All right, for number one, we have the square root of 25 minus 4 times 2 times 6. Now, the reason I have this particular problem here is because we're going to see a lot of problems that look like this, of this form, where we have a number minus something times something times something. Okay, you'll see that in the future. But we're going to simplify this. Order of operations, we don't want to do the square rooting first because we have something inside the square root. We have we're subtracting here. We don't want to subtract because we're multiplying all those first. So we need to multiply that first. Negative 4 times 2 is negative 8. Times 6 is negative 48. And then we have the square root there. And then we subtract those. 25 minus 48 is negative 23. And then we need to simplify that. Well, now when I go to factor that, negative 23, the only factors that I can think of are negative 1 and 23. 23 is a prime number, so that's the end of the branch there. And so we only get negative 1 times 23. There's no pairs here. So we can't take anything out using prison break, but because we have the negative 1 there, we can take that out. That would become I radical 23. So that is number 1, okay? For number 2, we have some big numbers here. We've got negative 3, square root of negative 1,500 or 1,500 a cubed. Well, the negative 3 we're going to ignore for right now. We'll bring that in later. We want to factor the negative 1,500. Here's how I'm going to do that. I'm going to put the negative 1 down, and then I'm just going to write down 1,500, and I'll do the cake method, okay? I can divide that by 3, so that's going to be 500. I can divide that by 5, so that's going to be 100. I can divide that by 2, so that's 50. Divide that by 2, so that's 25. I'm running out of room. Divide that by 5, I get 5. And divide that by 5, and I get 1. So I got a lot of numbers here. I got 2 2s. I've got a 3. And I've got 3 5s. Running out of radical. Okay, and then I also have a cube, so that means a times A times A. All right, so let's go ahead and circle our pairs. We got a pair of 2s, a pair of 5s, and a pair of A's. So we got a 2 that goes out, we've got a 5 that goes out, and we have an A that goes out. And then we'll write our square root here. What stays in? Well, the 3 stays in, the 5 that's alone stays in, and the A that's alone stays in. And then this -1 here, let me go ahead and underline that. That -1 is going to go out and become imaginary. So it's going to be times I here. So simplifying that just a little bit, you end up with 10ai radical 15a. And that is the simplified form for number 2. All right, let's go ahead and take a look at the next slide here. I guess I should just make sure I'm right. Uh-oh, what did I screwed that up. Because remember, from the very beginning, we had -3 out front. I forgot to bring that down. So we have to multiply that back in there. So -3 times all of that becomes -30 ai radical 15a. Now, notice on my lesson here, I've got the I going before the A. It doesn't really matter. Either way, just knowing I is the square root of -1. All right, let's go ahead and take a look at some operations that we can do with imaginary numbers now. Okay, operations with imaginary numbers, or what we call complex numbers. Complex numbers is combining real numbers with imaginary numbers. But the idea of adding and subtracting and multiplying and dividing, all the same rules apply as apply to polynomials. So if you know how to add a polynomial, 2 polynomials together, you'll know how to add imaginary numbers together. Okay, so let's go ahead and take a look at an example of this. It says to simplify the following. So for A, we have 9 minus 3i minus 5 minus 4i plus 6 times 2 plus I. Okay. All right. Now, how do I simplify that? Just like if I was an x, we would simplify this the same way. We're going to distribute, we're going to combine like terms, and we're just going to go with it. So remember, when we have parentheses here, we want to distribute the 1s that are out front. In this case, we're going to distribute the 6. So we distribute the 1 in here, and we end up with 9, and then minus 3i. And then for the second one, we're distributing the -1, so that's going to be -5 plus 4i. And then for the last one, we're distributing the +6. So 6 times 2 is 12, and 6 times I is 6i. From here, we're going to combine like terms. So I've got 9, I've got -5, and I've got 12. 9 minus 5 is 4, plus 12 is 16. And then the -3i, the 4i, and the 6i go together. -3 plus 4 is 1i, plus 6i is 7i. And so that is our answer. Now, I know what you're thinking. Don't you always put the x's first if you're going to put it in standard form? So if it was like this, if it said 16 plus 7x, we would flip that over. We'd say 7x plus 16 and call that our answer. And that's true for variables when we have variables. But remember, I isn't a variable. It's an imaginary number. So the standard way, the normal way of writing complex numbers, numbers with imaginary numbers, is that you have a real number and then you have your complex number. Okay, so that's just the standard there. All right, let me double check and make sure I'm correct on that one. We do get 16 plus 7i, so that's good. Looking at B, we've got 8 plus 3i times 4 minus 5i. Now we're going to see something kind of cool here. We multiply this just like we always do, right? We separate this out, so we say 8 times 4 minus 5i plus 3i times 4 minus 5i. And then from here, we'll distribute just like we always do. We end up with 32 minus 40i. And in this case, 3i times 4 is 12i. And then 3i times -5i. Now, here's where it gets interesting. Well, 3 times -5 is -15. And I times I is I squared. Okay. Now, from here, we would simplify. So we can combine our i's. These are like terms because they're the same variable with the same exponent. So we got 32. -40i plus 12i is -28i. And then here, We got negative 15i squared. So that's as simple as we can get it according to the rules of polynomials. But the one thing that we can do different in imaginary numbers that we can't do with polynomials is deal with this I squared, because we know what I is. And in fact, we know what I squared is. Remember, I'm going to write it down here. Remember, I squared, the square root of negative 1 is I, and I squared is negative 1. I told you had to know those two things. Well, here I see an I squared. So I can replace it. I know what I squared is. I squared is negative 1. So I can replace this with negative 1. I'm going to substitute negative 1 into that. And then now you can see I can keep simplifying a little bit, because negative 15 times negative 1 is positive 15. And then I have the negative 28i and the 32. And now these can combine. The 32 plus the 15 can combine. 32 plus 15 is 47, and then minus 28i. And that is our final answer. Okay? So really what you got to be careful of is when you're multiplying complex numbers, you're going to end up with an I squared somewhere. If you see an I squared, you can replace it with negative 1, and then you can keep simplifying. Now, if you see an I, you can't replace it with anything. That's not going to make it simpler to work with. It's actually going to make it more complicated because it's a square root. We don't want to put square roots in here if we can avoid it. But we can combine those, okay? All right, with that said, double check my answer here. I end up with 47 minus 28i, so that's good. All right, it's your turn now, so go ahead and try these 3 problems. And when you're done, come back and compare your results to what I have. All right, for number 3, we have 7 radical negative 54. Well, we're going to factor the negative 54 to negative 1 times 2 times 3 times 3 times 3, I believe. 9, 27, 54, yep. And then we still have that 7 out front. I don't want to make that same mistake. We're going to circle our pairs. We got a pair of 3s. So we got 7 times 3 on the outside. The negative 1 can be turned into an I. And then square root of what's left over is 2 times 3, which is 6. So 21i radical 6 is your answer for number 3. For number 4, we have negative 10, there's the bell, minus 8i minus negative 5 plus 3i. Now here we're adding these or subtracting them, so we're going to distribute that 1 out front. So we end up with negative 10 minus 8i, and distribute this negative 1 out front. So we end up with positive 5 minus 3i. And then we'll combine like terms. So we have negative 10 and positive 5. Negative 10 and positive 5 is negative 5. And then we have negative 8i and negative 3i, which is negative 11i. Now, we don't have an I squared here. Uh-oh, can't see what I'm doing here. We don't have an I squared here, so we can't simplify this any further than we already have. If that was an I squared, then we could replace it with negative 1 and keep going. For number 5, we're now multiplying these complex numbers, or we referred to them as binomials when there was x's instead of i's, but these are called complex numbers in this case. All right, from here, we're going to expand this. We're going to rewrite this as 12 times 4 plus 7i plus 5i times 4 plus 7i. And then we'll distribute. So 12 times 4 is 48. 12 times 7 is 94i. 5i times 4 is 20i. And then 5i times 7i is 35i squared. Combining like terms, we got 48 plus 114i, if I did that right. I think I did that right. Plus 35i squared. And remember, we can replace the I squared with negative 1. So that's going to say plus 35 times negative 1 plus 48. And then that's negative 35 when I multiply those out. And then combine like terms, 48 minus 35 is 13 plus 114i. And that is your final answer. All right. With that said, if you have any questions, please comment below or find me in a tutoring session, and I will talk to you all later.